Okay, good morning, everybody. We're back for another tutorial day. And we have two new instructors you're going to see today. The first is going to be Tom Clooney, is going to talk about the calendar. Then later on, Eric Wolf's going to talk a bit about radiation, which is also extremely important. Both of these are very important for those of you that want to run non-Earth-like planets. And then Geronimo Villanueva will join us in the after, or just before lunch rather, to talk about making observables with the model using planetary spectrum generator, which is supported at Goddard Space Flight Center. And then finally, after lunch, Chris Coloz will go through a step-by-step instruction on how to create a new planet, which should interest any of you. So, Tom, why don't you go ahead and take it away? Do you want me? I can't hear you. You're muted. It says you're muted anyway.
And I was halfway through sharing my screen, so it wouldn't let me unmute at that point.
There you go. Oh, you want to share your screen?
It's up to you. If you want to drive from your end, that's fine.
Can I drive it from my end? I think it just makes it easier. So let me share. Or actually, why don't you go ahead? I'm sorry. Go ahead and share your screen. That's fine. Why not? Let's do that. I apologize.
Okay, can you see that?
Yeah, looks good.
Should I do like a full screen? Is that what that button does? There we go.
Yeah.
Except it ruins the font. Oh well, we can deal with it. All right. So the basic strategy in
hold on. It says exit to click to exit full screen. We don't see your stuff. There.
Oh,
you have to leave it there.
Okay. I'm not sure what happened to the font since I did all that, but it's anyways. So the basic idea in how we manage this in Model E at this point is there is a separate notion of absolute model time, and that's stored in some integer way so that we have complete control. There's no round off involved in that. And then we want mechanism to go between that and the status of the orbit, and between that and calendar. So by orbit, we mean things like the distance from the sun, hour angle, declination angle, and such that determines the illumination of the planet. And for the calendar, it's things that are more human friendly, which are things like year, month, day, day of year, hours and seconds. And this is how we get our various different diagnostic quantities and such. And so it's important to have some notion of what these mean for our exoplanets. Okay, so continuing on. The basic approach we wanted to do, this is largely driven by Gavin Schmidt, was to keep the way we talk about the calendars as analogous to what we do with Earth as possible. And so to that end, we divide the year into 12 months, just as we do for the Earth. And in particular, we make the angle that is subtended by the planet during each month the same as the angle subtended by Earth during that month. So in other words, February will tend to be a shorter month for any given planet. And July will tend to be a longer month for any given planet, precisely because of that correspondence. But at the same time, we keep the time of year at which the spring solstice occurs, spring equinox occurs, so that things can get very interesting if you have a highly elliptical orbit and the apex of that orbit is maybe not as orthogonal to the equinox as it is for the Earth. So you can still end up with February being a longer month or July being a shorter month because of the eccentricity effects. But for relatively circular orbits, you're going to tend to get the description I gave initially there. Then within a day, we divide that up into 24 equal hours. Now, this is different than some other groups have done. Some people have treated hours as more of a physically defined quantity of 3,600 seconds. That's not what we've done in Model E. There's 24 hours, so however long the day is, we chop that up into 24 hours. And it's a few other just, things like, the hour angle is 180 degrees, so that we have midnight on January 1st is actually midnight for your planet. One other little note is we adjust the period of the orbit so that in the usual cases, I'll give the caveats in a minute, we adjust the period of the orbit so that it's an integral multiple of the number of days of the planet. That's just so that we can have a simpler calendar without anything like a leap year. Okay, now, what I described on the previous slide, which is the defaults, works really, really well for Earth-like systems where the rotation period of the planet is much, much faster than the orbital period of the planet. All right, when that happens, we can have an integral number of solar days per year with only having to do a very minor adjustment in the length of the year. and dividing the year into 12 roughly equal months anyways, you have a lot of days in each one of those months. So our notion of what a day and how that relates to seasons and stuff like this keeps that separation of time scales that we're used to thinking about. But if we go on to slow rotators, those assumptions break down and we have to do something to make the model more useful. So what we do in this case is the calendar will always have at least 120 calendar days. But once you get down below 120 physical days in a year, then the notion of a calendar day and a solar day are no longer tightly coupled. All right. So if you start looking at diurnal diagnostics for a planet that rotates that slowly, be wary that those diurnal diagnostics can be misleading. And the slower it goes, the more misleading those will be. Even monthly averages can be misleading at this point. You could have a month where one side of the planet is mostly day and one side of the planet is mostly night if the planet is rotating slower than, say, less than 12 rotations in a year. Then there's even a more extreme problem when you get to things like Venus, where the day is actually shorter than the year, or at least comparable to the year. Now, doing that trick that I said at the beginning, where we actually adjust the period of the orbit so that it's a multiple of the period of the day, doesn't give you accurate physics. So now we have a flag to deactivate that adjustment. And now even yearly diagnostics start to have a problem, right? Because a year no longer even finishes a day. And so you probably have to do a run of many years in order to get sensible diagnostics out of that kind of scenario. Ideally, what you want is the least common multiple of the period of the year and the period of the, that should have been physical day, not calendar. I apologize. There should have been a day in here. I never caught that. And this is the third time we've done this. So basically, you want something where the number of days and the number of years both come out to be integers, and then you've got good statistics. The problem, of course, is that these things are not integer multiples of each other, so you have to just take some approximation. So I think for Venus, Mike did something like 10 years or maybe 50 years in order to get reasonable number of, roughly the right number of days, right number of years in the stats. Okay. So how do you control all this? So the framework is very, very constrained to make it hard to activate the planetary things. We didn't want to have any of this stuff interfere with the people doing Earth climate. So if you don't override the planet name, then none of the other features I'm talking about here get invoked. It will then use the defaults for Earth, okay? But if you do set planet name to something else, and you can just say not Earth, even if you want to do something close to Earth, name it something else, then all these things can be used. So you can specify the obliquity for the planet in degrees, and the default value even then is the same as for Earth. Likewise, the eccentricity, again, default for Earth. Longitude at periapsis, again, default for Earth. The sidereal orbital period and the sidereal rotation period, those are in seconds, okay? And remember that this, I forgot, boy, 3 years and I'm just now spotting some things. I'm pretty sure that it's the orbital period that is adjusted, not the rotational period. I need to check on that. And then there's the quantization, which by and large, you're not going to want to change this unless you've got a very slow rotator like Venus. And then equation of time, which has a fun backstory. So with the Earth, the equation of time, for those of you that don't know, has to do with the fact that the obliquity and eccentricity themselves have some effect on when noon occurs on any given day, right? There's this slight wobble in the Earth on top of just the elliptic aspect of the orbit. This is pretty small for the Earth. It's order of 10 to 15 minutes in size when noon occurs on a given location on the planet, and isn't actually included in the Model E Earth system originally. But we had some scenarios, especially with some resonant orbits, where this is an extremely important effect. So we had to go implement it. And I hadn't fully thought it through the first time I implemented it. So we unfortunately have what I'm calling the naive option, which there's no reason to use, but for backward compatibility, it's the default on Planet 1.0. You probably want on if you want it at all. And just remember that for high eccentricity, slow rotators, this effect is quite large. And then the things you don't use very often, you can specify the mean distance, but bear in mind that Model E is already doing something else with distance in terms of how it deals. There's a factor, I think it's SOX, that deals with elimination. So you can oftentimes get the same effect by modifying that parameter. And that's the one that people that use Model E most often tend to use. And then our angle offset is if you actually have, some other notion of how the prime meridian is related to other topography on the planet, you may not want to use the default where the prime meridian it's midnight at January 1st. Mike Way can probably try to justify some use cases for that. I've already forgotten why we needed it, but you generally won't want that. We don't actually know topography for these other planets, so we can make a prime meridian where we want. I think it's like Mars where somebody else has already defined it and that's not what we wanted or something.
Yeah, I think the main use case, Tom, was for tidally locked planets. If you have topography on the tidally locked planet,
okay.
you want the substellar point to be in a different part of the planet. You set this hour angle offset, basically.
Right. Okay. Yeah. Thank you for the reminder. So anyway, so that's what's there. This is the stuff you really need to know, and it's you can look at examples for other planets to sort of see what people have done. So, any questions? Okay, well then I'll let you all go. And while I'm thinking about it, I'm going to go actually fix these things I spotted in the slides this time. So
there is one question in the chat, Tom. Do you want to take
Okay. How does the model quantize year if sidereal orbital period is shorter than the sidereal rotation period? Again, that's an extremely slow rotator then, right? So in that case, you want the, you don't want the quantization. The quantization still works the same way. It'll force I have to go look at the details. I think it'll generally round up, so you'll end up with a tidally locked planet. So it's 1-to-1, but I'm not entirely sure. But if it's that slow, that's not what you want, unless you want tidally locked.
Yeah, for example, if you're doing a 3-2 spin orbit case, you wouldn't quantize because it's not an integer number of days, it's 1.5. So if you quantize, you'll probably end up tidally locked. It's no good.
Right. Or with the wrong resonance, one of the two, but yeah.
Yeah, remember this model will let you do things that Kepler would not allow you to do. Just so you know. So you have to be intelligent about your use of these orbital parameters. Otherwise, you'll get garbage in and garbage out. So be careful. Okay, great. Thank you so much, Tom. That was excellent. Can you stop sharing?
Yes.
Next, we're going to move on to Igor Alienov. Igor, do you want to share your screen, or how do you want me to do it?
Maybe I'll ask you, but the next slide actually was in your name. I don't know, maybe you should just skip it, boundary conditions files. I'm not sure. Probably like more hands-on.
Yeah. Yeah, we'll move on from that.
Yeah. Okay.
You want to share your screen? You want me to do it?
Maybe you do because
Okay, so I can move past the Mars stuff and move to
just
this
move to
slide.
the
Okay, let me share the screen. Here we go. Okay, hopefully you all can see that.
Yes. Okay. So I want to talk first about how ground hydrology is implemented, and then I will show a few slides how that basically has effect on Mars and basically what you do for Mars specifically. So this is a general slide. So sorry, it's very busy, but it was made by a colleague of mine who likes busy slides. So this picture that you see is basically, first off, I guess I should say, I should just repeat how we partition our surface in our model. So basically, there are three major parts of the surface. It's ocean, and then what we call land, and what we call land ice. And land ice is completely different thing. It's those are permanent ice sheets. It's only like for Earth, it's only Antarctica and Greenland, and those are currently treated in somewhat simplistic way, in the sense that they have thermodynamics, of course, all the like water cycle and runoff, but they're not dynamic in a sense that they don't change their fractions. So basically, there is ocean, there is land ice, and I will not be talking about those. And the third part is land. That's what I'm going to talk. And the land is also separated in two things. It's basically just dry land and lakes. And those can be changed dynamically. So I mean, that means that lakes can grow and shrink and disappear. So I will first talk about dry land. So this picture here shows how dry land is modeled. And the main thing about dry land is that there are also two fractions of it, which are also not dynamic right now. It's bare surface and vegetated surface. So you have to reset those fractions. How much is vegetated, how much is dry. Vegetated surface has 16 plant functional types, so you can specify that many different types of vegetation. And this plot shows basically all the fluxes. It probably misses still some. It's I'm not asking you to like, read this plot and understand everything. It's just to show you complexity of the problem. So it's all these arrows are fluxes of heat and the water between different types of land and atmosphere, and between those this plot is even doesn't show snow, which also is on the ground and also can be on the canopy. So all of those basically are exchanging fluxes with each other, and the basic structure is that we have 6 layers of soil up to 3.5 meters depth, but that can be changed in the config files. But I advise you not to do this because the model was tuned for this particular depth, and upper soil layer is 10 centimeters. It basically was tuned to produce a reasonable response to diurnal cycle. So it also don't change it until you know what you are doing. Then the model has 3 snow layers. If you have snow is dynamic, so it can appear and disappear. Then there is a vegetation canopy layer. As I said, there could be 16 plant functional types. They basically occupy different fractions of the cell, but it's all like statistically mixed. I don't see it in basically in the output. There is a evaporation from all land types, soil, snow, and canopy, wet canopy, so the water on the canopy. Then there is a transpiration through the canopy. It's water taken by the roots from the soil, and soil has infiltration downwards, capillary uptake upwards, and there is a runoff from each layer, and the runoff goes directly to the lakes. Then lakes basically defined by the balance, water balance. I mean, the size. It's soil runoff, evaporation, precipitation, and also we have rivers in the model. So there is a transport of lake water between the cells by the rivers. Lakes usually are not allowed to have more than 95% of the cell area. That means that doesn't mean that you cannot define lakes which are 100%, like Caspian Lake can have like cells which are completely flooded. But when you have dynamic lakes, once they shrink, they will not expand back to 95%. That's just the way we treat communication with snow on the ground. We always want to leave some space for the snow. So it's kind of hackish, but it works in most cases, and we will fix it in the next generation model. But so far, just keep in mind that if your lake expands, it will not expand for the entire cells. And
Igor,
yeah.
Does evaporation transpiration from canopy include effects on wind, of wind?
Well, it's what's called aerodynamic. I guess that was Nancy's word, but yes, that means of course that it's in direction with atmosphere. It's just standard basically evaporation formula. I guess everybody is using. Yes, it's turbulent transfer coefficient multiplied by wind and multiplied by gradient of basically saturated water water pressure minus water pressure in the atmosphere. So that's the standard formula. Yeah, and lakes are assumed to be conical right now, but there are also other options. Though probably not of them are available in Planet One, but
I think it's not in 1.3.
yeah. So it's conical lake, which I think we enabled also the thin.
If it gets too small,
Yeah.
we just ignore it. The lake fraction will be 0, but the lake, the water is retained.
Yeah,
sort of
so
hidden away until enough additional water comes into.
yeah, we didn't put cylindrical lakes here.
Sorry,
We didn't put cylindrical algorithm here. The one.
yeah, we did.
Okay,
It says that. So it becomes.
Yeah, but that was probably nicest wording, so it's, I guess it's for the future. So Planet 2 definitely has cylindrical lakes also, but that's probably not enabled yet in Planet 1. The idea is basically when your lake becomes too shallow so it's cylindrical when it's big, but the tip of cylinder basically is cut off and replaced by tip of the cone is cut off and replaced by thin cylinder, so that basically you don't get lakes which are too shallow. And but you probably don't need this information right now. So yeah, so lakes probably in Planet 1 don't evaporate completely, but they disappear from the map in a sense that if you have amount of water in the lakes below a certain amount, this water just sits in the soil, but it doesn't have any area. So you basically have to accumulate certain amount of
evaporate.
Yeah, you have to accumulate certain amount of water before the lake becomes visible and before it starts to communicate with the atmosphere. Yeah, and usually you're supposed to define river directions to for rivers to flow between the lakes. If you don't specify those, the model will not crash. It will just assume that there are no rivers. So basically, each lake becomes local and accumulates all the water that basically is available, and basically the water is removed only by evaporation. But you can also enable automatic river directions, which will be based on topography. This option is on the slide. So if you specify this option in your run deck, then you will have rivers, and they will be just decided from topography. So it will be rivers will be going from uphills, downhills, pretty much. So I think that's all that I wanted to say about this slide. Can we switch to the next slide?
Yeah, I was just gonna say that this last bit was implemented by Rudy, who's here in the room with us.
If you use that next option, river has another advantage. Let's see, if there are the points where there is no if there are boxes where there's no outflow, without that option, there is an emergency outflow if it's too high, so which didn't work too well. In this case, if there is no defined outflow in the river direction file, then it for that box, it creates, it decides, depending on looking at the neighboring boxes, it decides in which direction the river will flow. So we will no longer have these towering lakes that suddenly flow out and then build up again and then disappear again. So it's a better option.
It's a sophisticated option.
Yeah, even if you have river directions, it's a better option.
Thank you for that implementation. It's greatly appreciated. This was sort of backported in a sense from the next version of the model,
Right.
which is very useful. Okay, thank you,
Yeah.
Igor. Let's move.
Well, yeah, I guess one thing I want to say, like,
Yeah.
since most people probably will be working with plants without vegetation, one thing that is missing, but maybe is important, and we are going to implement it some point, that basically all the evaporation from the soil happens from the upper layer, from the first layer. And though there is a capillary uptake, it's kind of slow. And also if your model is cold and everything is frozen, then basically there is no uptake. So basically the algorithm which is missing is evaporation from the lower layers. If you have cracks in the soil, that sometimes may play important role. It's not that important for Earth, but it may be important for planets which are cold, or for the planets which have thin atmosphere below the triple point of water, where basically you don't have liquid water. If there is no liquid water, then basically there is nothing to move in the ground. So one has to keep it in mind, and also there may be a glitch in the soil, that water may still be moved even if you're below triple point. So treat the triple point, treat the behavior of model below triple point like with caution, and check what it's doing, because basically it was written for Earth. We are fixing these things. They probably will be fixed in planet 2, but here it's still kind of important. Yeah, and also keep in mind that infiltration infiltration is fast, but capillary uptake is very slow. So sometimes your soil will equilibrate very slowly. Like if you start from the wrong initial conditions, like you have completely saturated soil, but it should be dry, it will dry slowly. Runoff certainly helps, but if you have completely flat surface, then yeah, it may take thousands of years to get a perfect equilibrium. So keep that in mind.
Igor, there is a question. Is there subsurface water? I know the answer, yes. Does surface water balance include percolation into subsurface?
Yeah, that's what I call infiltration. I'm sorry, I guess maybe I'm not very good with terminology, but yeah, but infiltration, I meant water going down, basically based on, well, pretty much there is just hydraulic diffusivity of soil, and it depends. Actually, one thing I didn't mention, that there are different, there could be 5 different, I'll talk about this later, but there could be 5 different types of soil textures. Yeah, it's on the slide. Sand, silt, clay, there is also peat, and there is also bedrock. Bedrock basically means just impermeable. So the water movement will depend on soil texture. The hydraulic conductivity will depend on it, and capillary uptake is computed by computing matrix potential, for those who know what it is, and it's basically proportional to gradient of matrix potential. So yes, the water moves up and down. Important thing is that the bottom boundary is impermeable. It's kind of like a limitation of the model. Different models may do it differently, but ours is impermeable. So runoff is only kind of going basically horizontally out of the soil layer. Yeah, and runoff depends on local slope. I think I'll talk about it in another slide. So I guess that's probably all about this slide.
Okay,
Yeah,
to the next slide.
Yeah, so this slide basically repeated slide. It just shows you at the bottom input files which are associated with ground hydrology. So VH file is vegetation fraction files. So that's basically the fractions of different vegetation types, plant functional types, what we call them. And then there is top index file, which is called top index, but actually just standard deviation of topography, which is needed for some computations. And there is soil file which defines soil textures and the slope of the local slope. Rough is roughness length, but you can skip it, and it will be computed automatically from topography. But if you know it, it's better to specify because you will get more precise answer. And soil IC is is a file where I specify initial conditions. There are actually two ways to specify it. I think we talked yesterday that there is GIC file, ground initial conditions file. But if you look at GIC file, you will realize that you don't know what it contains because it's kind of like a core dump type of file. So it's that file is good to use. Basically, if we provide such file, you can use it provided that we describe what it's doing. It's difficult to construct this file. Usually we don't construct them by hand, but it's more like we take basically a restart file which was dumped by the model and extract the ground hydrology. So it has complete ground hydrology information, but not very easy to modify by hand. But soil IC file, that's which is listed here. That's basically the file that created for you. So it's very easy to construct. I'll show later what's inside. Basically just the main quantities. So I think I'll skip the next slide. Yeah, so okay, so this is just contents of soil file. Basically just NC dump for you. If you just type NC dump on soil file. So now I'm talking, for as an example, I'm using the files which we use in Mars Rundeck. So soil all sand means that it's basically set to all sand, all textures were set to sand. So that's what you see inside this file. So lat long, those are resolutions of the model. NGM 6 is number of soil layers, and I said there are 6, and 5 is IMT. Those are textures of the soil. So you specify basically those in terms of fractions, so they have to add to 1. And below are the variables which you have. So the important is DZ is thickness of layers. Basically, don't modify those, just use whatever we use in other input files. This just tells you what is the thickness of the layers. Q is soil textures. So they have to add to 1 for each cell, and as I mentioned, that then you calculate or rock. Q and QK, they're kind of the same thing. It's a little like package that introduced. Well, actually, they were needed earlier, but now QK is nearly never used. So basically, just assume that it's the same quantity, but you have to set it. So those are just so textures, as I said, and SL is a typical slope. Typical slope of the ground in the model in your current setup. Just look at the numbers which we are using. It's actually tuned to produce the right runoff. So basically, your runoff will be sort of like proportional to this value. So start from what we are using, and if you have no idea what to use, the rule of thumb would be just to look at some of the Earth Rundeck of the Earth input files and pick a point on Earth where you think topography is similar to your planet, and just use that number. That's what we often do. I guess that's all about this file. Can go on. Yeah, so I see. I wanted to talk about this. This are your input. This is your input data for soil. So again, at the top of the resolution. So basically, specify just 3 variables: it's wetness, snow, and temperature for all 6 layers. So wetness is basically how wet your surface is. 0 means no water at all. 1 means completely saturated. One thing to keep in mind is that that soil cannot be completely dry because there is what we call hydraulic, hygroscopic water, which cannot be removed from the soil because it's basically just chemically bound to the soil. So the model automatically adjusts the amount of water when you start the run. So even if you set wetness to 0, it will add some water to satisfy this hygroscopic requirement. So your model will have some water, but it will not be removable. So it will not go to the runoff. It will not be removed by evaporation. Though honestly, I guess there are some leaks in the algorithm. So don't expect if you set everything all water in your run to exactly 0. Don't expect that there will be 0 everywhere. There will be some small amounts going around, but they should have no effect on any physics. Snow is just thickness of the snow. It's specified in terms of water equivalent in meters. That's basically how thick water would be if you melt the snow. And temperature is just temperature in degrees Celsius for each cell. For each layer, you specify what's the temperature. Just make those numbers reasonable. Keep in mind that snow amount and temperature will be basically will be changed quickly because the model will equilibrate. Soil wetness is sort of like more important because that's the amount of water you specify in the model, but the amount of snow and temperature is just to start the model. Otherwise, the model will equilibrate. So just start with something reasonable. Otherwise, the model may crash because like very high gradients and the stuff. Okay, I guess. Oh, that's why it causes it. So can we
That's for later.
yeah, can we jump back to the Mars? Yeah, this. Yeah, I think that's it. So this basically just wanted to say a few words. Do you still have time?
Yeah.
Yeah.
Like
Do you still,
6 minutes.
so I just wanted to say basically how we start Mars run. That basically will include both information about what Tom was saying and something that I just explained. So basically how you set up things in the run deck. So this basically just repeats what Tom was doing, but this gives you a specific extract from Mars run deck, how you specify Mars parameters. So you specify a planet name Mars that and you set it in CPP definitions. Planet params like Mars that basically enables planetary algorithms, non-Earth algorithms, and you give planet name just for your records. Then yes, you specify eccentricity, obliquity, longitude of periapsis, sidereal rotation period, sidereal orbit periods, sidereal rotation periods. Those are all set for Mars. We specify quanta year true because we have like over 600 days for Mars. So it's fine to quantize it. And here we specify mean distance from the star to define the radiation. As was mentioned earlier yesterday, that we usually consider that the best way to specify insolation is to set planet as 0 parameter. But you have to specify just one of those, not both in your index. So keep in mind, just use one approach and another. For Mars, it was just so easy to specify the distance from the star, so that we do it. For any non-solar system planet, you should use planet as 0 because planet mean distance is basically scaled with respect to the sun, with respect to basically
It's going to inspect the installation at Earth.
Yeah, yeah, but I mean, it makes sense only for solar system because yes, it will, if it's one, then it will be installation of the Earth by the sun. So yes, it's just multiplied by basically Earth solar constant multiplied by 1.5. Yeah, so can we go?
And it's
next?
the solar system of present day, not the past solar system.
Yeah, yes, it's, yeah, I was talking about modern Mars. That's exactly like, yeah, because we also model ancient Mars. And this just to show you what you'll see in your PRT file. It's basically repeats the same information, which we specified in the RunDeck, just to show you what to expect to see in PRT file. So whenever you specify a new model, new planet, or even when you use our RunDeck, which we have provided, it's a good idea to check to see that all the variables you specified printed correctly in PRT file, that PRT file understood what you were doing. And actually, one thing I wanted to mention about PRT file yesterday, but didn't have time. At the end of the setup run, or when you first start the model, when you look at PRT file, at the end of it, it will list you the RunDeck variables which were not used, like warning variable such and such was not used. And that is useful check for you to see that you spelled all the names of the variables in the RunDeck correctly. Because if you see something is not used and you specified in the RunDeck that basically warning for you that maybe you misspelled the name or you are using some variable which actually maybe was not implemented, maybe we listed it for planet 2. But usually we don't do this, but anyway, check to make sure that you don't have unused variables there which you expect it to be used.
Yeah,
Okay.
I think we should stress that. So this is in your rundeck.prt, the name of your rundeck.prt file that'll be in the decks
No,
run
it
ID
will-
directory. So it's always good to double check these things, as Igor was saying. We cannot stress that enough. When you make a lot of changes to these run decks with hundreds sometimes of lines, you might make a typo or make a mistake, and you want to make sure that you've done things the right way. So always check these PRT file output in these sections to make sure that the parameters you've set have actually been set.
Yeah, and I
It's more
apologize.
forgiving than the name list.
Huh?
It's more forgiving or more, it doesn't like, unfortunately, a name list that just stops the run, crashes the run if you misspell something.
Yeah.
In the parameter section, that's not the case.
Yeah, in parameter section, since it's in-house algorithm which reads it, there are some disadvantages. So basically, yeah, if you misspell something, then the model just explains that it's just some variable which yes, you specified in the RunDeck, but you don't use it in the current run. That's kind of allowed, but you have to keep in mind. So it's always good to look at PRT file. Even 90% of it will look like garbage to you, but try to make sense if you see some warnings.
Absolutely. Because there are some parameters that are used only with certain modules in the code. It's not used in other modules. So sometimes they're used, sometimes they're not. So it depends on what you're doing. So it's a very good idea to always check this file, make sure it's set to the things you expect it to be set to. We can't stress it enough, obviously.
Okay, this again, the output in PRT file is just nice to see basically what Tom's calendar is doing for Mars. So that's what yeah, basically is printed in your PRT file, so you can check. Like you'll see that the number of days in each month. That's yeah, that's the first column. It's like close to between 50 and 60. So yes, you have months which basically have 60 days instead of 30 that you are used to on Earth, and you will see often some printouts or warning messages or error messages which would say like on March 45 the model crashed. So don't be surprised. It's a normal output. Yeah, and on the right, those are basically the major orbital parameters which will be printed out also, so you can check that they are what you expect them to be. Yeah, I guess next. Yeah, this is basically how you said Mars. I'm just showing you Mars topography, so that's from topo file, the Atma variable. So basically just elevation in meters. So that's what we are using in Mars. Next slide. All this is just to show you what Mars is doing, but Mike already showed it before. This actually, unfortunately, is not implemented yet in Planet One. But Planet that's the result of Planet Two.
This is from Planet One. This is from our first paper. This is in.
Yeah, that's Planet One.
This is
Yeah,
lighter side.
Oh, but this by with
but
community
it,
changes.
You can make these changes.
it's uncommitted change. So
Next
this,
slide.
yeah. So that was showing you how CO2 condenses, but unfortunately in Planet One it's not too condensing. So I wanted to show you then this slide. This is how you said Mars albedo. We use test albedo. Well, I think in the example around deck, it's still just a uniform albedo, but you can download this albedo file from our data portal. So anyway, problem or the feature is that in our model we don't set there is no input field like albedo. Albedo is based on the information which you specify in which file. Which file contains all the vegetation types and also two types of bar soil: dark bar soil and bright bar soil. So for planet like Mars, you of course have no vegetation, so you just have two types of the soil, and you have to set them up properly to get the right albedo. So bright soil is assumed to have albedo 0.5, and dark soil is albedo 0. So basically, specify those two fractions to get the right albedo, and in theory, you can even specify the amount of bright albedo greater than 1 and the amount of bright soil greater than 1 and dark soil negative because they have to add to 1 just to get albedo higher than 0.5. But I wouldn't recommend to do this, but I think the model will still work. But usually it's very rare cases when your planet will have more than 0.5 albedo for bare soil. And on top of that, of course, you will have either snow or CO2 frost. So the final albedo is shown on the right bottom. So basically, here you see have CO2 frost on the northern pole. So it's very bright albedo, but the rest of the planet is basically what you specify for bare soil. So it's mixture of dark soil and bright soil, and that is supposed to represent test albedo as it was measured for the month. And I think that's it.
That's it, yeah. So thank you very much, Igor. So we'll take a break now and we'll come back at the top of the hour and Eric Wolf will talk to us about radiation. So see you all soon.
Mike.
Yeah, you need to stop sharing it. Then.
Yeah.
Yeah.
Okay, y'all, we're going to start up again and our radiative transfer expert, Eric Wolf, is going to talk to us. Eric, do you want to share your own slides or you want me to share the slide?
What do you think is better?
It's up to you. You can do it.
Okay, yeah, I'm going to try to do it. So, hi everybody, I'm Eric Wolf. I'm the radiation person for ROCKE-3D. I apologize for my absence. I errantly, or rather, my beautiful wife errantly made a vacation schedule for us during this time period. So I'm calling in from the West Coast at the moment. I'm normally at CU Boulder in Colorado. And let me get my slides going here. All right. Let's see. Share screen. And okay. I've had a little bit of trouble with, tell me if this looks okay. I've had a little bit of trouble with Keynote on my personal computer showing this funky bar on the side. So if you're seeing that, I apologize. I'm not really sure how to make it go away at the moment. If anybody has any tips.
It's working okay, no worries.
Okay. So thank you guys. So as part of ROCKE-3D is Socrates. So Socrates is a long backronym for the suite of community radiative transfer codes based on Edwards and Slingo. And that is the radiative code that we use with ROCKE-3D. It's actually a separately created code out of the UK Met Office, which a previous worker with ROCKE-3D, David Amundsen, linked. This was about 6 or 7 years ago at this point. So why are we devoting a whole section of time in the tutorial just to be discussing radiative transfer? Well, radiative transfer is one of the pillars of a general circulation model. So radiative transfer determines the radiative energy balance. That's the solar energy from your star coming into the planet with its stellar energy getting reflected away by clouds, scattered away by the atmosphere, absorbed by different gases in the atmosphere, and then likewise also your thermal component of the radiative energy being emitted from the surface of the planet, and then you have the greenhouse effect from your different gases, CO2, methane, water vapor, clouds are a greenhouse gas. Radiative transfer is also computationally a very expensive piece of the model. So it's one that we have to take care in doing, not just correctly, because naturally you may think of, naturally you may assume, and you'd be correct, that the radiative balance is a key component to determining the climate of the planet. But we also need to make sure we do it fast enough. So for exoplanets, we need to make sure that the radiative schemes are, or for any planet, for Earth or whatnot, we need to make sure these radiation schemes are fast enough, and also for exoplanets, flexible enough to handle a wide variety of atmospheres in a minimal amount of computational time. And so this is not really a trivial exercise in trying to balance these two. So when we think about, so Earth-based GCMs tend to be tuned, built only for the Earth's atmosphere. You have the sun, which we know the spectrum of, and then we know the Earth's composition. And then for climate change related studies, we know that CO2 is within a really narrow range, cosmically speaking, quite a narrow range. If we're thinking pre-industrial CO2, 285 ppm up to a doubling or two of CO2. But for exoplanets, things start to get different. You change your star, which can have significant effects on how you treat your radiation, especially for these M dwarf stars, which are significantly redder and push the peak of radiation out into the near infrared. And then you also change up your different gases, a lot more CO2, more methane, different weird gases like hydrogen, that all have to be accounted for. So this brings in Socrates. So Socrates was developed at the UK Met Office. It was linked to ROCKE-3D in 2017 by David, or 2016, sometime before then, by David Amundsen. And Socrates allows for interchangeable, what are called spectral files, which help facilitate the flexibility of the radiation problem in the ROCKE-3D GCM. So the spectral file is really the core concept to Socrates, and particularly for somebody who isn't, intimately involved in radiation and knowing, Socrates is a great code. It has a million different options. You can do different types of two-stream approximations and has all sorts of different options that you can play around with. But from the general user perspective, the spectral file, that's what you're going to be thinking about. So the spectral file is composed of a pair of text files, which are read in at runtime in the model and fully define the radiative transfer treatment. So the spectral files are separately defined for both the long wave and the short wave. And this is novel compared to other radiation schemes. So I've worked with a lot of different codes, and they all have a set radiation bands, set radiation gases, set which gases absorb in which bands. And Socrates is different because you can read all of that information in at runtime. So what's in a spectral file? So I've started to allude to that. You have the number of spectral bands, or your spectral resolution, which has to be specifically controlled for GCMs. So as a little bit of an aside, in doing GCM radiation, you can think about, you want to do it good enough and fast enough, because in a 4x5 model, like as our typical simulations in ROCKE-3D, you have 3,312 columns that are called to do radiation. Now, we don't call it every time step, we call it every few time steps to save computational time, but you're calling the radiation millions of times over the course of a run. So line by line radiation models, which go through every single spectral line, are more accurate, but they are way just orders of magnitude too expensive. You can never use them for your GCM. So we need to make models with bands on the order of 10 to 30 bands per shortwave and long wave stream in order to be fast enough. So the next thing, the spectral files also include are the absorbing gases, and these are cast into K coefficients, which I won't dive into. K coefficients, you can look it up. It's a way of how they one takes the line absorption and actually reorders them into an ascending function, and makes it easier and more computationally efficient to do the absorption calculation. And then baked into this, you have which gases are in which bands and how many Gauss points, these are the K coefficients, are needed per band in order to get an accurate answer. And these are all tuned to a specification of your atmosphere, whether it's Earth CO2 or Mars CO2 or whatnot, for instance. The spectral files also have your pressure and temperature ranges. It also has things like your water vapor continuum, also tuned to your specifications. Excuse me. It also has collision-induced absorption, which is important, say, for Mars-type atmospheres where you have CO2, CIA, as it's called, tuned to spec. Cloud and aerosol optical properties. It also does subspectral grid weightings based on your input, stellar spectra as well. So we create these different spectral files tailored to different atmospheres, different stars, and different planets. And we provide them publicly through the ROCKE-3D team. So currently we have a number of different spectral files to use. And I'll go through them pretty quickly, but feel free to email me and ask me questions. Again, I apologize, I haven't been around for the tutorial, but feel free to reach out and email me if you have specific questions. So we have, generally speaking, we have our Earth through time spectral files. These include the present day spectral files with the names GA and DSA, a Proterozoic spectral file. So I'm working on this now. This should be done hopefully by next week, which is sort of an intermediary file between from going a little bit further back in time from Earth. So we have moderate CO2 and methane, but it also has O2 and O3. And then we have our Archean spectral files going 2.5 billion years and backwards for Earth's history, where there was no oxygen, but we have up to very high CO2 and high methane, also H2 and N2O, other things like that. Our next set of spectral files are Mars through time. And these consist of two spectral files of Mars and then PM, which is Paleo Mars. And Paleo Mars, the Mars spectral file is pretty much just CO2 and water, where the Paleo Mars starts to incorporate more exotic things. We have hydrogen is a big component. We also have methane and associated collision-induced absorptions in those. And then finally, we have this group here I'll call other worlds, which are sort of novel, offbeat, if you will, spectral files listed below for Titan, the early moon, and the Hadean Earth. And even though these have all been cast into the Earth through time and Mars through time, that doesn't mean that they're not applicable also for exoplanets. It actually turns out when we think about exoplanets and habitable exoplanets that the majority, probably 98% of our conjured atmospheres end up being able to fall into one of these little boxes. So for instance, if you're thinking about the outer edge of the habitable zone, some cold planet orbiting in a distant orbit and with a dim solar irradiation, well, that's really kind of the early Mars problem, right? So you could use a exoplanet with a high CO2 atmosphere using one of these Mars files, a paleo-Mars file, for instance. So in addition to the core spectral files, one also has to, and it's a small sub step, if you will, in the process of spawning a new spectral file with a new stellar spectra. And the reason why this is done is because there is a subgrid scale weighting scheme that improves accuracy. Because due to computational constraints, we have to have wider bins. So right, we can't have 1,000 bins in our spectral resolution. It would be too slow for the model. So we have 10 or we have 30, 20 to 30 in the shortwave, which is a common number. Socrates will do a weighting step where it weights the absorption in each larger bin based on the slope of the spectral irradiance within that bin. So we've created a number of different stellar spectra here. You can see grouped of Earth through time. These are based on Mark Claire's models. Now, there's not a huge difference between the sun 4 billion years ago and the sun today, as far as the spectral content. We know that the early sun was dimmer than today by up to 25%. Spectral content's not terribly different. Normalized to a given stellar constant, you're talking a watt or two difference between them. And then there's the late K and M dwarfs. These are a focus of a lot of our exoplanet work because these are the best targets at the moment for us to observe things around. So we have a large amount of late K and M dwarfs, including famous planets, famous stars such as Proxima Centauri, 80 Leo, TRAPPIST, and so on. We also have, before I go on to the next one, we also have some red giant stellar spectra, and then we go up to about 7,000 Kelvin. This is in your F dwarf class. Now these are synthetic spectra. There's a little caveat down to really go to hotter stars. We need to monkey with the bins a little bit because you begin to push some of the radiation out of the short end of your spectral grid. So our spectral grids tend to go down to like 0.2 microns, 0.25 microns. And then once you get above 7,000 K, you start to push a small percentage, starting at 7,000 K, maybe a percent or so of radiation out the shortward end, and you miss it. So to really go to hotter stars, I'd have to rework some of the spectral files to include an extra bin or two shortward of 0.2 microns. But we can just, if that's of interest, contact me, we can discuss it. So some rules and guidelines for choosing spectral files. I think this is important. This is probably, as a user, the thing that you're most, will most be relevant. If you're just trying to use the model, you're not trying to dive in Socrates and the linking. And as an aside, before I go through these, with the flexibility of Socrates, which is very unique amongst GCM radiative transfers, to be able to read in this entirety of the spectral file as a text file at runtime. It is great because you can make things flexible on the fly. Of course, that means you need to be able to, the downside, if you can call it a downside, but the price of that's probably a better way to put it, is you need to be able to create the spectral file beforehand, which is not a trivial step. But fortunately, as I've shown, we've made spectral files that cover pretty much the gamut of simulations that one would want to do with ROCKE-3D. So the rules and guidelines for choosing one. This is where it gets a little confusing because you say, okay, we have the model. You can't just run it. You actually have to think critically about which spectral file you want to pair up with your simulation. So Number one, choose the spectral file which best matches the specified gas components of your atmosphere. I might run out of time here, but I wanted to show, if I have time, I'll show, there's a document we have on the Google Drive, which goes through in detail the specifications of all these different spectral files. So, and generally a spectral file is okay to use for the stated constraint on the gas mixing ratio in question or lower. So if it says 1% up to 1% CO2, you can use it from 1% and below. 2, for computational expediency, choose the spectral file with the fewest spectral intervals that meets the atmospheric specifications of your run. So if you, generally speaking, when you look through the spectral files, the more complicated they become, the more spectral intervals they have. So for this is particularly relevant in the short wave because there's a lot of absorption in the near infrared region of the spectra with water vapor, CO2, and methane combined. So when you have high values of all of those combined with an M-dwarf spectra, it gets kind of tricky in that region, and thus we have more bands. So for the Paleo Mars file, we have, I think it's 46 bands in the shortwave. So that's the slowest of the spectral files. And that's because that assumes high values of all of those gases. So it's very complicated in the near infrared. Now, if you know you're doing a simpler, an Archean-like atmosphere, you move down the chain in our spectral file list, you'll see the Archean atmospheres have fewer spectral files than the Paleo Mars. And the Archean atmosphere has less CO2 and less methane. Moving further on down to the current Earth, you have the fewest number of bands. As the atmosphere gets, you have fewer greenhouse gases in the atmosphere. So, as I said, the radiation is a very slow part of the model. So you don't want to, you'll be more productive if you choose the most appropriate spectral file for your code that meets your specifications, but does not exceed them and become overly dense with spectral bands. So rule of thumb 3, be careful when switching between spectral files in a single study. So we've created all these different spectral files and they're all tuned to different values. That's how Socrates has a on the fly when you're creating the spectral files. You don't choose your own Gauss point. You're going Gauss points for the K distributions, which most GCMs, typically the user will choose 8, the same 8 in every single bin, but ROCKE-3D, or Socrates rather, tunes it and does a transmission test and automatically and tunes how many it needs. So it might need 2, it might need 15. And so because of this, all of our spectral files, small flux differences can exist in, I'll say, the connecting regions between spectral files. I'll give the example, for instance, the Archean spectral file AR versus the Archean spectral file ARCC. AR you're supposed to use for 1% CO2 and under. ARCC is 1% to 10%. But if you're running a sweep, parameter sweep of simulations where you have a simulation at 1% or 0.9% and then 1.1% and you cross over between the two, you can introduce an artificial hitch, small, very small, hitch in your results by switching between the spectral files. So in a case like this, I would say choose one, choose the ARCC and run both simulations with the same spectral file if they're close together and they kind of cross over a border of the spectral file specifications, and do that to avoid having an artificial hiccup between the two spectral files. So, and then 4, if in doubt, ask me. We can do offline testing to confirm or refute whether a spectral file is appropriate to use. So, and then Mike, I don't know if you want to cut me off, it's 8:20, or if I have time, I was just going to open up some of the common documents. But I think my time is up.
Maybe
So
we can just look at it quickly for a minute and then we'll move on to Geronimo. Is that okay? Just to show people what it looks like. But try to make it quick.
Okay. Okay. Let me see if I can do this new share. All right, I'm trying to be quick.
We have to unshare and then reshare. Yeah.
Did this come up? Did this switch?
Yeah, I see the Google Doc page.
Okay.
So click on
Good
that.
stuff. I'll be I'll be quick. So the first one here, we have your user's guide to Socrates. This is a description written by David Adamson years ago, describes how you select, where it comes into the rundex, the input files, what you put in a rundex for a spectral file, for the spectral file LW, spectral file SW, stellar spectrum, different things related to the connectivity between the two, checking the accuracy. That's a more complicated topic. I'm not going to dive into that. Changing the stellar spectrum, how you can create your own stellar spectrum and do it's an easy step to load up a new stellar spectrum. And then what I really wanted to show was this document here. So spectral files for ROCKE-3D. And this is where we go through all of what's actually in these spectral files. You see your pressure temperature ranges, typically 1 to 400. And I'm gonna kind of, go down through. The formatting got messed up there. I'll go back and fix that. Present day Earth, you see, and they got descriptions, and then Proterozoic Earth up to 5,000 ppm, CO2 Archean Earth, and so on and so forth. I don't need to go through all of these. And then finally, the last two, I won't even open up for your power users, if you will. There's a detailed user's guide put together by the Met Office, and then a detailed technical guide put together by the Met Office. So if you get into actually making your own spectral files, you're going to be looking at this user's guide to figure out what's going on at a deeper level. And then if you actually got into modifying the code or getting to advanced radiative calculations, that's where you'd start digging into the tech guide. So I'll stop there. And please contact me if you have any questions. I'm gonna stop sharing.
Great, thank you, Eric. That was excellent.
Do we have time for a quick question?
I think we have to move on. So Geronimo, do you want to share your screen or do you want me to share? You want to do it? Yeah, go for it. You're muted, by the way, so. You can put it in the chat when I'm done.
I'm muted now. Okay.
Now you're good.
Yes. Hi, everybody. Yeah, so let me go back right into this. Let me see. Can you see the slides?
Yeah, they look great.
Okay, great. So, well, hi everybody. I'm Geronimo Villanueva. I'm here at Goddard, and I'm talking about PSG. And some of you may have heard about it, but it's always how to connect ROCKE-3D and what PSG is about, and how do we put it together. So as we've been hearing from Eric, wire transfer can be used for different things. A GCM uses the wire transfer to make an energy balance. That means you need to take care of how the radiation comes in and comes out, and you try to make sure that you conserve energy in the right way. So it tend to typically the codes like Socrates, as Eric was talking about, they tend to encompass or are done to encompass a broad range of wavelengths. So you reflect the sunlight, thermal emission, and it's about pretty much energy conservation driven. But there are some cases that you wanna create a spectra with ROCKE-3D. You have a ROCKE-3D simulation, you have the state of the atmosphere, and you say, okay, how does the planet would look like if I would use, I don't know, James Webb to look for, observe the planet. And this is what PSG comes into place. So for the sake of, typically, if you ever use a dye sort or something like that, what Eric was talking was about fluxes. What I talk about here is about intensities, which are directional fluxes in one direction. So let's talk about what is PSG and how you can use it. So PSG is a kind of a multi-element code. It combines several aspects, typically for astronomical purposes. It has orbital calculators for exoplanets and solar system bodies. It has a lot of things for small bodies that we don't care, but for icy bodies like comets and stuff like that, and icy bodies like TNOs. But the main driver here is that it can model terrestrial planets and giant planets, and you can do coronagraphy and transit. So that's the main idea behind the tool. And as you can see, because there are all these different layers how you can use the tool, it can become a little bit, you have to have a learning curve. And I will try to go through here to talk about what are the things you need to care and what are the things you don't need to care. And some of the things that, mainly about the nomenclature that you may see across the website. So main thing is heavily used. A lot of people are using it for a lot of things. So we have reached, it's funny that it works on a small little computer. You will see that you will be amazed that this doesn't work in a cluster, but works in a computer, which I think is even slower than my own MacBook Pro here. And it's stored here in Goddard, and that little server handles all the traffic. So right refer calculations can be, as you see, very time computation expensive, but we've been optimizing them to run fast. But nevertheless, what we've been doing is that you can run it on the public server, but then you can want to also install it in your own machine, and or multiple clusters of machines, and do a full array of things beyond what you have in the thing. Actually, most of the users who use PSG now, they started their own machine, and I'll tell you how to do that. So one of the things we've been working, especially lately, this is something that we produced last year actually, is we wrote a book about it. It's kind of a handbook. It's more not a book per se, but the main idea of the book is to, first of all, have a little bit introduction how to use the tool, but also about the math that goes into the thing. Some of the things you get really frustrated when you use these things is that they're a little bit black boxy, and we wanted to remove some of that by explaining what goes into the code. And so if you know what is going on, you say, oh, this code is doing that and doing that. So you remove some of the black boxy. So it has been written in a didactic manner. So it's more like a textbook for university target. And there's a section at the beginning section, which is more about how to run the code. But the main thing is that we also make some videos, and the videos are, again, introductory. They kind of summarize every chapter. This is Sarah here talking on chapter 1. It explains how to run the tool and stuff. So I recommend that you go to the website and run it that way. So the main thing is that this is the screenshot of the website. The upper part of the tool is all documentation. So every time you want to learn more about the tool, always go to the upper bar, and then you can find the documentation about how to run the things and explanation about the tool. The main idea is that you also, if you might always say, so the tool is a tool, it's a web interface, but it can also run it with this code we call application program interface, which is probably what you're going to be doing. So this allows you to, you have a ROCKE-3D output, you have a Python script or any script you want, and it will take the output from the ROCKE-3D and pass it and create spectra. So you can automate it, do a scripting mode. And my always recommendations, first run it on the web interface on this, thing. It's not efficient, but, you get a flavor. Everything got populated in the right way. Once you get that up and running, you automate it with a scripting mode, and you should get exactly the same thing, if not is wrong. And then once you get that mode, you say, okay, I'm going to start it in my own machine. And then you start it in your own machine and do the same thing. And then once the free results agree, then you got it, and then you can fully automate it. That's normally the way I recommend running the tool. So the main thing is that, which I think is, again, as we've been talking about here, we're trying to model intensities. So you can run at a very high resolution, a medium resolution, a low resolution, and any resolution you want, but across all wavelength ranges. So what we've been doing in PSG is that we compile a lot of databases, line by line, correlated K, cross sections across the whole wavelength range. So you can take your ROCKE-3D spectrum, state, and then create a spectra at any wavelength. And the main thing is that you can also put the planet at specific locations in the solar system, or not in the solar system, an exoplanet, and then see how it looks like from abroad. And you can even do, you want to compare, you want to do even C2 simulations of a limb observation. You can also model that in a direct fashion. And the main, I was telling you, so the code works, so it's a right transfer code effectively, and includes correlated K, multiple scattering. So use effectively is a die sort, called a PSG dot, but it's an adaptation of die sort, and include non-LT and other effects. So I mean, it can have immense complexity. That's one of the things that is problematic. Can have immense complexity, but we've been trying to make the complexity to be reduced so it's accessible, and you don't have to go through, trying to reinvent the wheel here. And you can also, the neat thing about it is that you can also do simulation and produce noise. And this is something that a lot of people are using also for ROCKE-3D. So you create your spectrum, and you can pass it for an instrument like, LUBAR or have the Works Observatory. And then it will tell you also the noise performance from a coronagraph. And I think that's the main thing also you can explore. Again, my recommendation is that, first of all, simulate something that you know what you should get without any noise. See if it makes sense. Features you looked at as you've seen in a paper or something, once you get up and running, then you put you do the noise simulations and stuff like that. So the main neat thing about it is that it has this multiple scattering calculation. So when you compute scattering calculations, they are, again, very computationally expensive. Scattering, when we call multiple scattering, we refer that where a path of light hits a particle or Rayleigh or molecule, and then it hits another one, and it hits another one. So you have multiple impacting scattering processes. Typically, there are ways to do that. The most classical way is called the two-stream approximation, which is heavily used to get energy balance. And it works in many cases for Rayleigh and simplified clouds. But when you want to compute intensities at a specific location, you need the multiple scattering component, and that improves. You need to have many more streams. And that is allowed there. And then there are ways to mitigate that requirement. The problem is that the computational requirement goes with the n to the free. So, going from 2 to 10, you can see the massive impact on your computational time. But here you can see these are simulations for multiple scattering simulations done for Earth, cloudy Earth, Mars, and Titan. And these are done with not a lot of streams, maybe 4 or 5 tops. And you can already see that you can capture a lot of the general multiple scattering performances. So again, those are things that are embedded in PSG. You can actually compute this called DOM simulations. It will give you the full color, full view of the sky in this mode. Okay, the type of geometries. And again, ROCKE-3D, as we've been talking about, is mostly tailored for exoplanet modeling. But as you know, ROCKE-3D has a heritage in Earth. So you may even want to run Earth simulations with PSG, and if you want to do things like that. So there are different types of geometries. What we call the orbital in situ, that includes nadir, limb, anything that you are flying around the planet or on the surface. You can be on the surface of the planet looking up. So that is one type of geometry you can do with PSG. Another one is observatory mode that's probably going to be looking at. And this is important that you see this keyword here. There are 2 type of observatory modes, and it depends on the distance. So when the distance is less than 0.1 parsecs, PSG, we assume you are within the solar system or within the confines of our own environment, and the star is not in the field of view. And by that nature, is only the planet by itself, and there is no star around it. I mean, it's there, but it's not in the field of view. Once you are going away, when you are a little bit further out, then the star and the planet start to be similar in the similar field of view. And PSG will start to look around if it's in the field of view, and it will try to add it or not. So all those things are done by the geometry model. It's important you get that right, because sometimes you can see the planet or not in the right place. But the main idea is that if you have a big field of view with a telescope, you may see the planet and the star together in the same place. And this is just to tell you the different geometries. You mostly will work on the observatory mode, which is the one there. And then there are other ones, if you want to do, they are more specialized. And there are, if you have an orbiter and you want to make simulations of limb, you can also do those. Okay, but the main complexity is that, again, we've been talking about here about ROCKE-3D, which is a 3D code. But normally what I like doing is first starting with a 1D code. Or assuming that the planet is homogeneously the same everywhere. And that is, again, it's the lowest starting point. So typically when you you have a planet, you have a planet that you look at the planet, you are looking at different emission, you have different incidence and emission angles at each place. So the sun shines in different places at different points on the surface, and the direction towards you is different. So because of that, you have to sample it. Normally with the GCM, you have the information pixel by pixel, so you can create a spectra for each single pixel and then aggregate them all together. Imagine that you have a low-res GCM, or actually you have a one-dimensional spectrum planet. Then you have to homogenize it everywhere, and then you have to divide. So PSG has a thing called subsampling mode, explained in the handbook. It divides the planet in little parcels, and it computes spectra in an optimized fashion to have commonality of emission and incidence angles. Again, the spectrum of a planet will be defined by the incidence and the emission angle. So having a good diversity of incidence and emission angles will add realism to the calculation. Of course, the more points you add, the more computationally time it will take. Okay, but the main driver of this talk is about the 3D aspect of it, which is the globes we call. So there is within the PSG framework, there's an application called GLOBS, or Global Emission Spectra, that has this web interface, which is nice because you can visualize how the parameters of the GCM appear. And that allows you also to see that, the way the numbers are ingested into PSG are meaningful. So these plots here are what we call of GCM files or PSG GCM files. So effectively what you need to do first is take the ROCKE-3D, convert it to this binary GCM file that PSG understands, and then you can upload it to PSG and you can see things like that. If that conversion process went through well, you will see things that are meaningful. If you see the planets in the wrong place, or you see the continents not appearing, or you see the winds all in a funky function, is because some of that didn't go well. So normally what I do always, run the script, make sure that I got the conversions, upload it to PSG, see if I can see the winds and stuff coming up in the right way. That worked well. I know that PSG is understanding the GCM data in the right way. And I will show you in a little bit in a demo how to run this. There is also the PSG GitHub. So it has the source codes from most of the important codes, like the multiple scattering, the PSG dot, and other scattering things are there. The right transfer elements are in the website. But I think what you mostly care is this one that says globs there. That is what we've been compiling, Python scripts. And again, we've been always adding more of those. And those are Python scripts that allow you to take the ROCKE-3D output and make it a PSG format. And there are some explanations here how to, if you click on the thing, you can actually see what it does. Similar to what Eric was saying, there may be some learning curve there. If you have any doubts, let us know. We can help. Send us an email. But the main idea I recommend is to look at these scripts because they are allowed to provide the interface between the GCM data, the netcdf file, and what PSG will do for the right transfer. Okay, so the two modes that you're mostly going to be carrying is the transit modeling. So we have papers about it, and I recommend you look at these papers because they kind of provide a little bit of a, they're examples, but they provide some framework. How do we use them? How do we, what type of things come out? So I recommend you look at those papers because also, if you ask me, if you want to do a first simulation with PSG, is to try to match some of that stuff and make sure that you get similar units, similar things. That means that everything is running in the right way. So we have a few papers, and I can, I just put saying also because we've been validating the code heavily. There's always this, competition between right transfer codes so they're all the same, no worries. I mean, I think everything was developed in the 50s and the 60s, and all of us, what we've been doing is just pretty much, a little bit work in the 70s and the 80s, actually. But we've been pretty much compiling that knowledge base and creating tools around it. But knowledge base wise, everything's been done decades ago. And there are a few papers that I would recommend you take a look to that. But another thing, which is, I think, again, I think is the main driver of ROCKE-3D, is the choreography and the reg modeling aspects of you can do with PSG. And again, we have a few papers. I recommend you go for them. Choreography is particularly very difficult to understand what it is. It took me time to actually learn more about it. I'm still learning about it. So I think I would recommend, in the handbook, we have a documentation about it. First of all, understand what is choreography. How does it work with your data? How those numbers are propagated into the thing? Because there's going to be a moment when you run a simulation, you're going to be like, what is coming out here? It looks like garbage. So I recommend you learn about choreography with the one-dimensional code first. Make sure that you replicate some of these papers and then move to the 3D scenario and see how numbers change. But I definitely recommend you start with 1D case here. This paper by Jade is actually, for me, is this latest paper here with Jade is the one which I think is the nicest because it's a 1D code, it's a 1D simulation. But in that paper, we compare LUBOR, HAVEX, the different modes, and we compare different noise models, Ty Robinson's noise model and the PSG one, and we do a lot of comparisons there. So my recommendation, again, look at Jade's paper, replicate a 1D case. These are Earth at different stages. So we have a early stage of Earth and then modern Earth. So I think I would recommend you go with that one. Do a 1D case, see if you can match the spectra and the noise. And if you get something meaningful there, then move on to the 3D case. Some of this paper, this is already going to 3D. We use Wacom here. And again, I recommend you explore some of these things that have been happening there. Okay, just I need to explain a bit about choreography again, just so you know how that is propagated into PSG. So effectively, what you have a blocking element in front of the star. You have the planet, and what you do is you have to create a spectra at every point on the planet. Every little point. You aggregate all the flux of the planet, create one single spectrum from the planet, which is the aggregate of all the points across the surface of the planet. And then you have the flux of the star. You have the two sources of light. Each of them will go through different optical path, different, we can call throughputs. Then they are affected by different things, then they get added together, and then they go through the detector. So this is what this diagram is showing. There are like two optical paths, and then they get added together. Learning about that is important because you're going to be looking at units of contrast and peculiar units that are familiar, and it's important that you familiarize what the code is actually doing internally to see, oh, this number means that, and how the noise get out of this. And then again, we have benchmarked heavily the choreography, Ty Robinson's and other codes. So again, it's important for us to, if you get a number that is kind of meaningful. So we have done a lot of validation on the choreography transit codes. So the noises are okay for future observatories. If you want to run a simulation with James Webb, I do recommend you use the ETC or things like that, more official tools. They have more subtle elements of the detector. You can do a first guess with PSG, give you a flavor of this is fully out. But then I would recommend that you do a first pass with PSG and then go to the official ETCs to get the actual sensitivities. So please consider using it. It's fully free. We have worked a lot and validated, and we produce a lot of documentation, and we always expand the documentation. And also, if you develop a script or something, please let us know. We can put them in the GitHub, and we can add more stuff there. So now it's time to go to the demo. Okay, so first thing I want to show you is the handbook. So open. So this is the website. This is the, if you go to PSG right now, if you go to this website, it looks like this. Normally what I always do every time I go to the website, I do reset. That means that what happens is this. Every user, every time you go to the website, you store a cookie, and I give you an ID. Every person has a cookie with an own ID. So every file you produce, anything you do will be recorded under that ID and only visible to you. I mean, I could look at them, but I don't, it's completely, there are so many that it will be impossible to know what is going on. So the main idea is that when you have this web interface, you are editing this configuration file, we call it. And that is what you're going to be doing with the scripts. So normally what you do, you create this, you take this ROCKE-3D and you make what we call a PSG config file that has the geometry you want, the composition you want, everything you have in that single text file that combines text file and binary information, the 3D information. So typically what you do, you have it like that, then you download it here. It will give you a file. Let me see if I can. That looks like, yeah, it looks like this. It has it's small, so it has all the fields. It looks a little bit cryptic. I know once you run it once and you have it, it's that way. Documentation about every field is here where it says remote operation parameter list. So it's everything is being explained. Sorry, and then you have all the fields explained here. Again, in the website, the upper fields are all documentation. So if you click in documentation, you have access to the book, and I will explain a little bit about that. And then more, about the model, how you define the profiles, the different databases and stuff. In the bottom of the website, there is the GitHub repository. If you, the Stocker, now, this is the GitHub. So if you click here, you go to the thing, and then you click on this one, and then you have the Python scripts. You see, this is from February 2021. Actually, we're working with Mike Way and Thomas Fauché and others on making new ones. So we will update on this. And again, let us know how this goes, and we can tell you more about it. Okay, so that's the general gist of the website. We will do an example later, but I want to introduce you to the handbook. So the handbook, it's again, it is being written as a textbook effectively. So the first section is the one that looks more like a handbook and explains more, how the web interface looks like, how the codes run. This is a classical handbook, we can call it. And it explains, how sections, you can, what is this section, what is that section, stuff like that. So this is more like a handbook classical way. But beyond that, then the other sections are more like a textbook. So this is a place you can learn more about what goes inside. You don't have to become a master of all these things, but I do recommend that if you run a few simulations that familiarize that, how the atmospheres are, what is aerostatic equations. I mean, pretty well, but just, go for that. How do we put it into PSG? How the write transfer works? There are, what are the components that go into the code? What happens if you have multiple scattering, single scattering, and no scattering, how the spectrum will look like. And then that is a guider to know what you're missing. You also, what databases are there, which molecules are, what is the broadening coefficient, and all those things. So I will ask you to look at the handbook and familiarize with those things, because it explains some of the things. Yeah, and some of the, how scattering works. Again, scattering is a very complicated to understand. Actually, I think I've been trying to model that for 20 years and I still learn about it because it's really complicated. I do recommend that go to the handbook and look at some of these diagrams, because it allows you to understand what a phase function means, why is the two streams approximation, what is 10, what are those definitions, and you may be able to get a better handle what those things are. Okay, and now let's go. Yeah, so that's a handbook, explains this information about the noise here that you may find of value when you want to see, when a model coronagraph model explains the noise sources and stuff like that. And the retrievals, you don't worry about that much, and how to run the API. This is how explains how to run the API, the documentation, how to install it. And if you one day create a cluster of PSG little machines, how you can orchestrate them all together to create like a mega cluster. We use that for the ExoMars mission. We have like 300 PSG clones running together. So if you have a lot of simulations to run, you can do something in that domain. Okay, let's go back now to the web interface. Okay, so I'm going to show you quickly the globs mode. So if you're here, it looks like this, but you want to go to the globs here app. And the globe apps will show you something like this. And I will actually going to go through different cases. So just for demonstrating, if you see this thing and say, what is all this stuff? I recommend you come here and pick one of these templates, 3D templates. And we have the ROCKE-3D one here. There's Earth with Mera. Earth, you can click on this one and it shows the surface temperatures plot here, the surface albedo. This is the area coverage and stuff like that. You can see it, and there are the winds. You can visualize things, nicely. You can see. So, I mean, if you have the data, you can get a flavor if the numbers are coming out in the right way. So in the case of ROCKE-3D, you can load it there. And you can see it. And if what you have done through, as I tell you, you have the ROCKE-3D, you have the Python script that makes the PSG GCM output. Effectively, as you know very well, ROCKE-3D will produce a lot of time steps, or you can have only the last one. So what you have to do is only create one state only. Say, okay, I want to have the last stage, maybe the convergence state. And you ask, give me the atmospheric state at that stage. And you create the 3-dimensional fields for all the variables that you care for the right transfer, pressure, temperature, abundance of molecules, and stuff like that. And then you come here and you put upload PSG GCM file, and then you put the file, and then it will come up. And it will appear here. If everything went well, you will see things that are meaningful. You see temperatures that are in the right format. If you see some squares and stuff, is something didn't go well. Okay, so then how do you go from there to spectra? So as I say, you have you have the geometry here, and you can do two things. I was telling you, you can do chronography, or you can do transit. So it's important to understand that in a simulation, let me see if I can go show this plot here. So if you do, this is what we call the phase, is very important. So if you are a phase 0, you are behind the star, and you are what we call secondary transit. If you're 180, you are in front of the star, you're looking at the night side of the planet, and you're in primary transit. You can have an inclination, of course, and then you can have different phases. So typically, if you do chronography, you're at what we call quadrature, which you are 90 to 70. And if you are in transit, you're at 180. That information appears in the geometry section appears here, the phase number. So if you change that number here, I'm gonna put it at 1 parsec. You can see this is the star, that's the planet, and I am at 45 degrees from the orbit. And if I come here and put 90, I am now in quadrature here. And if I'm in 180, which is transit, I am now in front of the star, and I'm looking at the night side in front of the star. So that tells you, the phase is very important. So if you're gonna do phase analysis, what you do is you modify that number, and you will get the phase. If you're gonna do a phase curve, for example. Okay, so that you got the transit, you got the coronagraphy. So for the sake of simplicity, let's do a coronagraphy simulation or something like that. So let's do phase 90. And then we are at phase 90 here. You can see we're looking at half night, half day of the planet. So everything lines up in the right way. We're at 1 parsec from the planet. In the geometry mapper here, we have the 3D information from the thing. It says that we want to do disk emission. You can click on these things to do primary transit, and it will move it to 180 here. You can see it changes to 180 the phase. Or you can say, look, no, I want to do 90 disk emission, and then it will change the phase and the geometry for you to be in the right way. Then here it tells you the composition, that the things that we have, we can change them. And again, for simplicity, I'm going to remove all the aerosols. It's all Spain, the comment, I'm adding and removing things. I just put some atmosphere here, and I'm going to put that, I don't know, one, for the sake of it, I'm going to put this thing about mostly made of nitrogen, CO2, and water. And we have a Lambert surface and a simple albedo. So it's a very simplified scheme here. We go back to the mapper here, and then we have the resolution and the wavelength range. So here we can say, we definitely don't want LADI. We can say, okay, 0.4, this is a huge wavelength range, 0.4 to 30 microns. We have a resolving power of 500. And just to start with that, we're going to include the and you can pick different units for the output. I'm going to pick this one, which is the contrast ratio. It's a flux of the star, the planet relative to the star. And we're going to save it. And we're going to go back to the mapper. And okay, and then this thing called bin. And I'm going to do 200 just to show you what that is. And then you run. Okay, you press that and it will run now. And you see you get a single dot at the center. So and you get this is how the spectrum looks like for the planet. You can see when you have a binning, what it does, it takes all the points across the disk and it will bin 200 points. So it will do a huge amount of, it will average the atmospheric conditions across all the points on the disk, and it will create a single profile, and it will give you one spectrum. So it's the average of the planet across the whole thing. If you want to do a quick test, do that. But of course, you have the 3D information. You want to have granularity across the disk. So for the sake of it, let's do 10. Okay, now it will take longer, of course, because now it has to compute more spectra across the disk. But just to show you how this works. And the neat thing about the web interface to run it first, okay, now I've been by 10, the ROCKE-3D stuff. And now you get these different points here. And if you click in each of them, you start seeing that this is the night side of the planet. That's why the reflective flux disappears. If you come to the day side of the planet, the day side appears and you can see more flux. You have the polar area, you have the Rayleigh tail, very prominent in these high incidence angles. So you get a flavor of the different spectra at the different locations. So again, use the web interface first to make sure that the numbers are coming out in the right way. Once you're happy, then you automate it with the API and stuff like that. So now I'm going to be more ambitious, and I'm going to say, okay, let's try to do them all. So PSG will complain probably, but let's do it. So there is a cap of 200 points per disk. This is mainly not to kill the web server. If you install the Docker version, Thomas asked me to remove that restriction. So we have removed that restriction. It will kill your own machine, which is not good either, but it will take, you can put up to, I think, 2,000 points per disk. And that allows you to have much more granularity. As you can see, it's taking longer. It's doing multiple scattering at every point, so it takes time. If you have a narrow wavelength range, of course, it's going to be faster. So that's something that you can play around with the resolution and the wavelength range to make it faster. So, and hopefully it's done by before my time runs out. But yeah, the idea is that you will see the spectra coming out, and then you can download the spectra. So the globes will produce two outputs. It will give you the aggregated spectra across all this. So what it does, it takes the spectrum from each of the points, and it will weight by the projected area of every pixel. And so that's a mathematically also complex operation, because you have trapezoidal transformation and stuff. And it will add them all together and give you the average spectra of the planet. And then it will also create an image with the spectra at every point. You can download and it will plot that. So I think I will leave it for questions now, and while this thing runs, and we can talk more. Thanks.
Great, thank you, Geronimo. That was fantastic. So this one's still computing for 5 to 30 microns, right?
Yeah, it's doing 0.5 to 30 microns. I think we picked that range, and it's now okay. Now it's finished, and you can see we got much more. I mean, I think it capped it to 3, so it defined that it has to be capped to 200, and you can see you have much more granularity on the points here. Yeah, Alec.
Yeah, suppose my planet has continents as well as oceans, and it's rotating fast. And you have plenty of these observation points. Can you demonstrate how, for example, the spectra would look like as time goes on, as the planet goes through one full rotation?
No, that's a good point. So yeah, you can certainly do. So normally what you will do in that case, Alec, is that, so here you can see that, look at this particular continent thing. So you have here, what we have defined in this particular geometry is that the subsolar point, where the planet is, the sun shines at a particular latitude and longitude. And then, but you can change that to anyone. So for example, if you have a fast rotating planet, you can keep the lat long at a specific place, but you as an observer, you can modify your view of the lat long of you, the sub-observer point. So you can play with those two parameters. If you have a fast rotating planet, you keep you keep the same phase, but you let the planet rotate under you, and then you take a lot of spectra. You compute a lot of spectra for each of them, and then add them all together and create the average of the rotation. Or you can actually take a spectra for every phase, and then add them all together. That is, you can also do that. Again, it's possible. It requires some little bit of learning how to do it. Some of that is explained in the Python scripts with the thing. But yeah, certainly you can do it, and if you got stuck, let me know and I can help you with that.
Great, thank you, Geronimo. Any other questions for Geronimo? That was a real tour de force demonstration, Geronimo. Thank you so much.
Yeah, and again, it's a tool, and there's some complexity. We try to make it accessible. One of the drivers of PC has been to make it more accessible, but there is a little bit of learning curve, and I recommend to look at the tutorials. The video tutorials are here. This is the book and the tutorial. I just go for them. I give you a flavor of how to run things.
Yeah, I can second that. I had an undergraduate thesis student who followed Geronimo's tutorials and got all of this working for her thesis project, all on her own. Just a tiny bit of help from Geronimo and Tomas. But otherwise, the tutorials, videos worked great, and the handbook. So thank you for all of that work, Geronimo. That's really made it useful.
Happy to hear that about Mike.
Yeah, so if my undergraduate thesis student can do it, all of you can do it. I mean, she's very clever, but still.
I guess there is a question in the chat about non-LTE.
Oh, yes. Okay, let me see the question about non-LTE. Well, I can say, yeah. So the non-LTE, as you know, is another complexity. What we do, there are two ways you can handle non-LTE in PSG. What you care for an atmosphere, what we do, you can provide non-LTE profiles. I don't want to go into much detail, but let me do quickly an example here. So there's this thing you can load here called Jupyter non-LTE, and effectively what you have is that for every here, this thing here, for every vibrational mode of methane in this case, there is a different population scheme. That's why non-LTE. And then once you have for every bidirectional mode non-LT, you can then do the full non-LT calculation in PSG. It's exotic. You need some sort of pre-computed non-bidirectional scheme. I do have a solver for that here in PSG, but it's for expanding commas, not for. I can show you here is the called commentary non-LT thing, and it will compute the non-LT. It solves the differential equation to get the state. And there's a Python script you can download in the GitHub how to do it. But again, it's a little bit exotic how to do it, and I can help with that if you are having an non-LT case.
Thank you, Geronimo. Okay. Excellent. All right. Well, let's take a break then. We have a 1 hour break in here. Thank you again, Geronimo. That was really fantastic. I really appreciate you dialing in and helping us out. And I'll see you tomorrow, of course. Okay, great. So we'll take a break for an hour and then we'll start up again. So see you all after lunch, or our lunch anyway. Okay, bye-bye.